Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, thank you very much. Can everyone hear me okay? Excellent. So, for those that don't know me, I'm Stephen Johnson from the University of Southampton. I've allowed some extra time at the end of the presentation for questions. But if you don't get an opportunity, I've included my email on the slides, and the slides will be made available. So what I'm hoping to cover today is a look at space situational awareness and how we're using it in a project called Clouds in Space. We're going to look at how we're using cloud compute behind the scenes to get the calculations done, and we're going to look at the architecture for that solution. Obviously, we're generating quite a large volume of data here. It's very interesting data, and so I've included a slide on how we're visualizing the data. And then we're going to take a little bit of a change, and we're going to look at a separate project, which is very different to the Clouds in Space project. We're going to look at an Astra project. And then finally, there'll be some time at the end for questions. So, what is space situational awareness? Space situational awareness is about gaining knowledge of the operational space. So this is the area of space around the planet that we use. So the area of space that satellites live in, the area of space that we use for space missions. And we need to gain an understanding of how this will affect missions, how this affects satellites. And there are a series, so space situational awareness includes a series of different categories, such as solar flares, space weather, atmospheric density, and more importantly, space debris. We have a project called Clouds in Space, and this focuses on space debris. So we don't deal with space weather and atmospheric changes. We only concentrate on space debris. And what I'm talking about with debris is it could be a satellite, working or not, defunct. This could be a piece of a rocket stage that's been left, or it could be a natural rock or a piece of debris. And we refer to all of them as debris or just objects. Now, there's quite a lot of focus on this. So President Obama has actually made space situational awareness one of his priorities. And the reason for this basically is that as humans, we have polluted our space environment to the extent that the pieces of debris that are floating around there now actually pose a risk to future space missions, and they pose a risk to the satellites that are already existing in orbit. So an example of this is the Cosmos and Iridium satellite collision. This was a defunct satellite that collided with an operational satellite. They're about 500 kilograms each, doing about 20,000 kilometers an hour. There's a lot of energy there, and it resulted in over 2,000 pieces of debris. Key thing about this is that all of these pieces of debris are then left in an orbit which many other satellites operate in, and they then pose a risk to other satellites from further collisions. We also, as an extension of this project, so you can imagine what we're trying to do here is we're looking at debris that's around the planet, but as an extension to this, it's not too far-fetched that we can look at what we call near-Earth objects. So a piece of debris going around the planet is effectively just going in an ellipse, and a meteorite is effectively going in an ellipse as well, albeit that ellipse is bigger. And what we're looking to do is to deal with near-Earth objects, and an example of this is the Apophis. Fortunately, it missed us last time. The good news is, in 2029, it will miss us again. Interestingly, it will pass between our geostationary satellites and the Earth, which, by all intents and purposes, is a very close call. Bad news, of course, is in 2036, there's a 1 in 250,000 chance that it will collide with the planet. And so what we need to do is we need to gain a better understanding of this this operational space area that we deal in. We need to understand how we can model where these pieces of debris are going to be, where these near-Earth objects are going to be. And the way that this works, basically, so in a nutshell, you have ground-based stations that are radio-based or optical, and they're effectively looking up at the sky, and they're looking for objects. This data is then catalogued, and it's published by SpaceTrack. And so SpaceTrack have this catalogue that you can download of all the known pieces of debris or satellites. And so what we're doing at Southampton is we have a project called Clouds in Space, and the key focus here, we have a series of capabilities that the project is able to do, and the first one is that we're propagating debris. So you have a snapshot of all these pieces of debris that are in orbit around the Earth, and we can propagate them into the future to work out where they're going to be. Now this in itself is a science, and we're using a series of different propagators, so you can plug your own propagator in. So the first task is to propagate these objects to work out where they're going to be. Now obviously, if you know where a satellite or a piece of debris is going to be in the future, you can then do some calculations to work out if there's going to be a potential conjunction, i.e. a collision, which is what we're very interested in. So the second focus of the project is collision detection, and that is effectively an all-on-all calculation where you're looking at all of these objects and you're trying to work out whether there's a conjunction, i.e. collision. The next stage is the near-Earth object. We're looking at, obviously, calculating the location of the near-Earth object, which is basically the same as just propagating a piece of debris. And you could imagine that in the future you could take our calculations which show where it would impact on the planet, and you could then put those into calculations which let you do disaster modeling, i.e. Tsunamis, land-based disasters. And so you can add that in. And finally, the new area that we're looking at is debris removal. And this is very much not a trivial problem. And so you could imagine if you were given $10 billion and told to remove the most problematic pieces of debris, which ones would you remove? And we're going to deal with that. That's what we're focusing on in this project. And a naturally occurring piece of rock, effectively. We currently are tracking about 20,000 objects. This is what's published using the SpaceTrack. And on the top right-hand side here, you have it doesn't come out very well, unfortunately. You do have, effectively every dot on this diagram is a ground-based station that is basically looking for debris. And every time a piece of debris passes, it's catalogued, its new orbit is added, and it's published. But the interesting thing here is that there are 19,000 other objects which we're particularly interested in. This is feeding back a bit. There are 19,000 objects that we're particularly interested in that are over 10 centimeters. And we're looking, and it is possible to be able to track those pieces of debris. But I think the more important thing is that there are about 500,000 objects over 1 centimeter. Now, bear in mind that one of the shuttle missions, the window was cracked and they nearly lost the shuttle because of a flake of paint that had been floating by. And we're talking about things now that are 1 centimeter, which we cannot track. But it's believed that the technology today and in the near future will enable us to track those 500,000 objects. And I'd like you to bear that in mind when we're looking at the architecture that we've chosen for this. So what I wanted to do for this presentation is basically to give you an outline of space situational awareness and what is it. But also, for those of you that are thinking of using cloud from any provider, I wanted you to get an understanding of the sort of the issues and the advantages that you stand to gain from using cloud. And if you're already using cloud, I'd like you to look at Windows Azure, which is what we've chosen, and I'd like you to see how we're using Windows Azure and what advantages we're gaining from using Windows Azure in clouds in space. So the first thing here I wanted to do is basically say, well, what is cloud? What are we getting here? So it's effectively pay-per-use resource. You can You can rent, if you want to call it that. You can rent a machine for 1 hour, or you can rent it for 10 hours. And the idea is it's provisioned really quickly, so you can suddenly decide, oh, today I'll have 10 machines, and you'll get it. And effectively, this means that you can have an unlimited amount of resources. Okay, it's not unlimited, but I put the dollar sign there because it's unlimited, but limited by the amount of funding that you happen to have. And I think there's a mindset here that if you can change your architecture such that you can think, well, actually, I can throw more compute at this. And so that's a key thing here. The other thing is, if we skip to the bottom, is there's no capital costs, there's no lead time. So when I apply for funding, gone are the days now where I apply for funding and I wait for 6 months for the hardware to be installed. It just doesn't work like that anymore. Final point is that if you architect well, always bear this in mind, if you architect well, you can have this trade-off between cost and time. So it costs the same to have one machine for 10 hours as it does for 10 machines for 1 hour. Now, you're never going to get an exact, it's never going to scale exactly, so there's always going to be an overhead here. But do bear in mind, actually, you could, if you architect well, you can scale well. And the middle point here is, what I often get asked is, well, actually, what's the difference here? What is this cloud? Effectively, I've got a data source, a data center, or I could just outsource. We've seen this before. And if you look at the cloud providers that are out there, they're buying their hardware in bulk. So they're doing it cheaper than you ever could, first point. Second one is that they can optimize the way they're administrating these machines. So they can have their optimizations there, and so the costs are by far less. And the third point is a very key one for me, and that is about the utilization. So if you have a data center, you're paying for that data center whether you're using it or not. And if you're not using it, you're wasting your money. And what the cloud providers are doing is they're effectively selling you an hour's worth of compute, and they're keeping their utilization exceptionally high. And because they can keep their utilization very high, they can effectively pull in more cash, so they can run the data centers very, very optimally. I wanted to drill down into this utilization a little bit more here. And I've got this graph. Basically, the red line here is basically, we're looking at this problem if you have your own data center. The red line here is the maximum capability of your data center. And the problem we're looking at here is called the hype curve. This is a very generic example. And so the hype curve goes along the lines of, you have a service, you have a product, you have a website or something, it suddenly becomes very, very popular, and you can't meet the demand. If you look at the very right-hand side of the diagram, you could actually say that, well, actually your data center is sized appropriately for the application workload that you happen to have. However, there's this big bit here where basically you have this under-resourced demand, and this can translate into unhappy customers if you're in that field, or effectively queues in science. So the red bit there basically equates to people that are unhappy. But the grey bit, or at least the bit between the blue line and the red line, is equating to wasted hardware. And this is where you are completely throwing away your cash. How does this relate to clouds in space? Well, remember we talked about the collision between the Iridium and the Cosmos satellite? This resulted in these 2,000 extra pieces of debris that had to be modeled, they had to be tracked, they had to be propagated. If we had a data center and we had sized it appropriately, we would struggle to deal with such an increase like this. And so that's how it applies to the Clouds in Space project. But there's another scenario, and that is this idea of burst capability. So if you have predictable or unpredictable burst capability, but you've sized your data center so that it can deal with it, so again, the red line is your data center capacity. You can see here, if you're talking about customers or you're getting your science done, it's all working fine. And you can deal with these blips in demand here. So you can deal with the fact that you're going to be asked for extra resources, and that there's no problem there. The problem comes that for the Clouds in Space project, SpaceTrack are actually publishing the satellite updates twice a day. And it takes anything, bear in mind it's not a full catalogue, it's only the ones they happen to have seen that day. So it could take anything between half an hour or 2 hours to process the updates to the catalog. And what we're talking about here is when a piece of debris goes past the ground station, it sees it, it's catalogued. When we get it in the catalog, we halt the propagation algorithm that we've got working on that. We insert the new trajectory, the new orbit, and we start the propagation again, which means that all the results that we currently have are effectively useless now, or at least they end up in an archive, much the way that weather forecasting is done. And so twice a day we have this demand, and if we had bought a data center, we'd be suffering again from these idle resources, which would be costing us money. And the third area that we're really getting an advantage is this idea of super scalability. So it's a little bit of a contrived diagram here, but bear with me. So the red line again is your data center capacity. And it's sized well, so if you're looking at the very left, it's sized well such that your application workload is being met. But you can see that the workload is increasing. And so the first thing to do is to upgrade your data center. So we have an upgrade here, and you can see that demand is still increasing. And the next upgrade doesn't actually arrive in time, so you end up with under-resourced demand, because upgrading a data center is very time-consuming. And so you run the risk of basically lead time on hardware, or lead time on upgrading your data center. And the final bit at the top here is that, well, maybe you can only upgrade your data center to a certain amount. So at the University of Southampton, we have a data center that runs all of the machines for the university. We have a supercomputer in there. Our last upgrade, we had to buy a new substation for the electricity that we're pumping into that. The next upgrade that we do, I have no idea what we're going to do. We might have to buy a new building. And effectively, you get to this bit where you can only upgrade your data center so much. So there are two risks here you're taking. One, you're not going to be able to upgrade in time. Two, you're not going to be able to scale. This is why I call it super scalability. You're going to reach some limit. And so how does this apply to clouds in space? Well, if you remember, we're tracking 20,000 objects at the moment. Potentially, we would like to track the 500,000 objects, and that will be coming online. There are efforts now to deal with how would you actually track this. And that's 500,000, remember, not counting any collisions. So there could be collisions which will add extra pieces of debris that we need to track. And so super scalability is very key to what we want to do. We don't want to buy a big data center now because we're not tracking that many objects. But as the objects come online and we get to see more, we'll be able to scale. The other point here is that I think it's often missed, actually, that when you're looking at a data center, yes, you can upgrade it, but have you ever tried to scale down a data center? You know, it might be the case that you want to scale down and you can't sell your machines back to your provider. Whereas with a cloud, you can suddenly go, well, I've got 10,000 instances here, but I want to scale down now, and you can use 8,000. So I think that's a very important point that you need to bear in mind if you're going down the cloud route. There are two other key points here where we're getting advantage. So we've seen three points where the utilization is of benefit to us, and how we're harnessing that. But there are two other areas, and the first one is data dissemination. This is very interesting. So this was touched on a couple of presentations yesterday. And that's basically, if the first time I read a paper and I see a graph, I really do want the underlying data for that. I want to be able to repeat that graph effectively. So you can imagine that the conversation is going to go along the lines, I look at the author, I email him, he finally probably sends me some piece of data, and I take that piece of data and I'm probably then going to copy it somewhere else, maybe a cluster or something that I've got, and then I'm going to do some processing on it. But the question is here, why did I copy it twice? What was going on here? And the chances are that I copied it twice, once because I don't have enough compute on my desk and I want to put it on my cluster, so I move it there. And what am I doing? I'm moving my data to my compute. And the question is, well, where does data and compute live together? And the answer is the cloud. And so what you can do is you can share data in the cloud. So you don't have to use any fancy mechanism. You can just open up some of your data and say, okay, I'll allow permission for these users to use my data. What happens here is very interesting because I can pay to store my data. So I'm paying to keep it in the cloud, and I'm paying for some of the I/O on it. But if you come along and you want to do some processing on that, all you need to do is you need to pay for some compute power next to my data so that you can process it. And that's very valuable, very valuable. It also divides up the costing, so it's handy if you're on funding. If that's an area that you're interested in, there's a data market section appearing in the marketplace, definitely worth looking at, and this is about how you monetize your data and how you share it. And the last point I have here is about algorithm development and validation. And this is where we're seeing an advantage by using cloud. So you can probably very easily see, well, okay, if you want to validate an algorithm, well, okay, you've got a set of test data you put in, you're checking it for some outputs, and we can run that in parallel. So, well, there's nothing clever going on there, but the cloud, it's handy for that. You want to rent machines. And the algorithm development is very interesting because it's very much a serial task. You do some coding, you run some tests, you look at the results, and then you probably go back and do some coding. You don't really tend to run this in parallel. And algorithm development is very time-consuming. There are some algorithms where there's a suitably large enough computation required, even for the test suite, that this running stage takes quite a long time. Or there's a sufficiently large amount of data there that it takes a sufficiently long period of time. And so we're looking at how we can use Windows Azure to help us with algorithm development by shortening the cycle. There's nothing fancy going on here. You're effectively just renting a piece of hardware for the appropriate time in your development cycle so that you can hammer on through your test criteria or whatever input data you're doing and accelerate the development of your algorithm. So the question I wanted to answer here, so the previous slides have all been about cloud in general, regardless of provider, and how we're getting advantage using the Clouds in Space project. Now, Clouds in Space project is based on Windows Azure. And the question I want to answer here is, well, why are we using Windows Azure? So cloud providers, I've split them up here into three areas. And the top one is an infrastructure as a service. And this is where, when I rent my machine, I'm actually just getting a bare bones piece of hardware. And it's probably a virtual machine, but you're getting a bare bones machine. You are the administrator of that machine. You are responsible for that operating system, and all you've got basically is access to a piece of hardware of some description. On the other end of the scale, at the very bottom, we have software as a service, and this is where you're not bothered about where the application runs or how it runs. You just want to consume the service. So for Clouds in Space, well, there isn't a service, so that rules that out. And in the middle, we have what I call platform as a service. And this is where you're actually renting a platform. So you're renting an operating system. And this is what Windows Azure does. So I'm not responsible for updating the operating system. A lot of that responsibility has been passed over to Microsoft. And so there's a key advantage here. So for the top one, infrastructure as a service, it's not big enough of a difference for me to warrant changing what effectively, I have some machines, I have a whole bunch of virtual machines at the university. Why would I trade them for a whole bunch of virtual machines that are just infrastructure as a service? There's no software as a service, so that leaves platform as a service. And for here, I can see that I really do get a benefit, because not only am I renting a machine, but I'm also kind of renting an administrator. So that's why we chose Windows Azure for the project. So I just wanted to briefly cover the Windows Azure features. So we're using compute and storage. Wow, that table's changed shape. The table that's here basically is pulled off. It's the pricing list that you see on the web page, so don't worry about it too much. But the point is that we're using compute, so you're ending up with a Windows machine, but you can scale up as well as scale out. So you can buy a bigger machine or you can buy more machines, and bear this in mind. So buying a bigger machine is handy for algorithm development, but buying more machines is very handy if you're interested in storage or bandwidth and you want to scale your application. For the storage, we're using blob storage, so this is effectively just storing blobs. Table storage, which was mentioned earlier, and table storage, I think it's badly named, to be honest, because when you say table storage, people think, oh, SQL tables. it's not like that. There's very limited transactional support, for example. You're only allowed 2 keys. But the beauty about it is that it really, really does scale. It scales fantastically. So we use table storage for a large amount of our data. Queues are very interesting in that, and you're going to see on the next slide actually, that we lockstep everything using queues. So queues are basically how we tell workers to start and stop. And SQL Azure, we're using it a little bit, and I've got a side note here that basically, if you're looking at SQL Azure, it's not just SQL in Azure. There are some fundamental differences here, but bear in mind that what we've talked about here with the cloud is we're all about the scalability. So if you've got a 50 gigabyte SQL database, don't go and buy a 50 gigabyte SQL database in Azure. I don't know if I wouldn't recommend that at all. How about sharding your database? So I think we're going to see a lot of work around database sharding, and what this is basically, so remember, one 50 gig database will cost approximately the same as 5 10 gig databases. You're going to get better I/O performance here, and sharding is all about taking your database and splitting it across across multiple databases, which helps you with performance. Excuse me. So yeah, bear that in mind if you're looking at SQL Azure. The image at the bottom right here is the locations of the data centers for SQL Azure. Bear this in mind. If you see they're kind of spread about, so that you could imagine if you wanted to do some form of failover or some form of redundancy for your particular area in the world. Have a look at this. So I wanted to give you an overview of the well, it's not an architecture diagram, it's more of an architecture and a workflow diagram, but I wanted you to get a grasp of what we're doing in clouds and space here and how it actually works. So the first thing in the very top left-hand corner, we have a worker. So every one of these squares, that's not the purple ones by the way, but every one of the colored squares is an Azure worker. And what we're doing with an Azure worker is we follow the pattern where a worker it consumes messages from a queue which tell it what work to do. It does the work, probably writes some data to table storage, writes some data to blob storage, and it does the processing, and then it writes out to an output queue saying that I'm done. And the idea is that these are all like Lego pieces, so we can move them around, and you can imagine that one output is the input for another worker. And this lets us change the focus. So this here we're focusing very much on collision, the collision algorithm, but it doesn't work like that. We have a worker for collisions, we have a worker for propagation. You can plug them together in any order that you like. Bear that in mind. And what we're looking at here is the final point on the very first slide, which was, how do you spend your $10 billion? What are you going to do with this $10 billion? And this is how you would answer it. So the first one, top left, is import a TLE. A TLE is a 2-line element. Interestingly, there's 3 lines in it, but the acronym still works. We import this, and this is the full catalog from SpaceTrack. Now, the catalog, remember, we only see pieces of debris when they happen to go past. So the catalog is all out of sync, and the first thing to do is to synchronize it, to propagate all of the orbits to a point in time. So let's say today. And once we've propagated them, the piece of data that we have, which is the purple one here, is a full catalog. So this is a catalog of basically every object. Once we have that, we can take every one of these objects, and we have to do, effectively, as an order n squared, we have to do an all-on-all comparison. Yes, there are filters that you can apply, but it's an all-on-all comparison. So you take every object with every other object, and you're looking like, does it collide? Nope. Propagate to a next point in time, does it collide? No. So we have a collision algorithm here. Interestingly, the caveat is that we actually know the orbit of the piece of debris, not the exact position of the piece of debris, so it's just an orbit. And we actually do a Monte Carlo simulation where we're seeding these 2 orbits with X number of potential satellites, and we're doing a collision based on that. So we end up with a collision probability list. You want to run this for multiple times, so for every time step, for every satellite versus every other satellite, you're wanting to run this so that you're eventually, at the bottom, you end up with what we call a top-end debris. And this is a list of the debris for your chosen time period and its collision probability. So we sort it by collision probability. So effectively, it's almost the most problematic pieces of debris. The interesting thing here is then that you need to take into account, well, remember, we're looking at spending this $10 billion. How are you going to equate this to some form of cash? So we have an energy calculator, and energy is almost the same as cash. So, but bear in mind, if you want to substitute the energy calculator for some other type of calculation, you just swap it in for a different worker. So the energy calculator goes through our top-end list and works out the amount of energy it would take to remove a piece of debris. Now, there are many different removal techniques, but the one that we're looking at here is basically where you have your piece of debris floating by, you put yourself, your satellite, or however you're going to catch it, into a similar orbit, and you play catch-up until you slowly get behind it and you nab it. You can't just stand there and wait for it to come by, because you're going to end up with more fragments than you started with. Probably your satellite in many pieces. So we've got the energy calculator. The next thing is like, well, what order are you going to remove them in? Because, you know, if A and B are close to each other and you want to remove A, B, and C, then the order is clearly A, B, C. And you can only remove a finite number. So it's like the traveling salesman problem. It's actually a traveling purchaser problem, where you've effectively got a shopping list. You want to remove n pieces of debris, and you want to get the best bang for your buck. You want to get the best value for your $10 billion. And what we end up with is a removal order list, and we then pump that into the lowest energy. So basically, we have a series of different removal orders, and they then calculate the one with the lowest amount of energy. And in the end, you end up with a list of satellites that are very high up in your collision probability list, but are in orbits suitably close to each other, so that you can actually physically remove them. You got to remember, so by the time you've spent your $10 billion and it's sitting on the launch pad, those are going to be the same pieces of debris that you're going to remove, that you initially thought you were going to remove. You need to rerun these calculations again. So I've told you that we're using Windows Azure, we're using the compute, and we're using the storage. But I feel that if you walked away today thinking that Azure is compute and storage, then I probably would have failed. There's a plethora of other features that are in there that are very valuable, probably as valuable as the compute and storage offering. So I've listed a few of them here, and they're definitely worth considering. So these are the ones that we're looking at using. So we have things like a virtual network. So we have a data center at the University of Southampton, and you can imagine that, we're not going to get rid of it. We're definitely going to the cloud, so what are we going to do? You need to have a way where you can mix your machines, where you can bring cloud machines into your network. And so there's virtual network technology. Content delivery network allows you to push data out to around the world, so if you want to distribute data, it helps you there. There's a thing called the app fabric, definitely worth having a look at. We're looking at the service bus, so this is a bus, an end-to-end, endpoint-to-endpoint communication. Key thing for us here is that you can have claims-based authentication on your service bus. So what this means is that, so if you're with organization A and I'm with organization B, and we want to share some data, what currently happens is someone usually generates some credentials and gives you an account with their organization. But the question arises, well, I'm not really happy with that, because who's responsible for that account? I now have an account for someone from another organization in mine, and I need to be responsible for that. Claims-based authentication lets you do a mapping between credentials, and so that you can say, if a user comes from this organization, I trust them, map them to this user. And you can do this on the service bus, which is a very powerful feature. There's caching technology. This was previously called Velocity, so it's a distributed cache. We've used this on HPC before, and we're looking at using this in Azure. There's the marketplace, which we talked about, so this is the ability to sell your data. And there are many more features. I think if there's anyone on the Azure team around there, we're looking at using, so the thing that's missing off of this list is some form of MapReduce. You have a thing called Dryad, which you can run on an HPC cluster at the moment, and this is effectively MapReduce. And for the Clouds in Space project, we would be looking at, towards the end of the year, we would be looking at some form of MapReduce in Azure. So hopefully Dryad in Azure, please, thank you. And so what I wanted, we've chosen Azure, and what I wanted to list here is basically some of the considerations that you need to take into account. So see, these are some of the learning points that we've made along the way. And the first one is that basically know your data. So are you allowed to export your data? There are some countries, Germany for example, which is very particular about where you store your data. So know your data. Your data is going to live in a data center somewhere abroad. Be aware of this. There's also a public network between you and your data center. So obviously there's security, there's bandwidth issues there. But you know, if the public network goes down, your service is still running. You're still hitting your 4 nines or 3 nines or however many nines it is. Your service is still running, but you can't access it. Bear this in mind. And if there is an outage, there's an SLA which lets you get some form of compensation. Have a look at it. See if that SLA actually does compensate you for the total cost of an outage. Clouds are multi-tenanted. You know, you might be sharing a machine with someone like me, for example. Are you happy with that? Think security. Everyone always raises security. Pricing. Pricing is very interesting. I don't think that a direct comparison is very easy because there are always promotional offers, and if you're comparing it with on-site or on-premise computational power, then I don't think we fully understand the total costs for on-site. So, you know, electricity for the admin's office and all these things. All these costs are very hard to equate. I often get this about vendor roadmap. Yes, you're locked in. You know, if you've picked a vendor, you're locked into that vendor, or some people certainly think so. So bear in mind that if your vendor doesn't upgrade then to some operating system that you want, for example, then maybe that could be an issue for you. Key takeaway here is that you need a flexible architecture. So the Clouds in Space project, each of these workers, we can glue them together in almost any order. You need a flexible architecture so that you can take advantage of, so that you can scale, for example, but you need to be able to take advantage of promotional offers. It's pricing, you need to take this into account. And it's very easy to say, okay, fine, I'll architect with pricing in mind, but bear in mind, pricing model changes quicker than your architecture can, so keep your architecture very flexible. Licensing, it's always a problem, especially if you pay per core, for example, and that's an issue. The interesting thing about these set of issues here is, we've kind of been here before. When you're outsourcing, it's almost the same thing. A lot of these security issues, they've been dealt with. There are answers for them out there. So, cloud's not some big mystery. There are solutions out there. So now, I wanted to give you, this projector really isn't very good. I wanted to give you some idea of what we're doing for visualization. So we have all these orbits, we have propagation, we have conjunction, we have quite a large amount of data here, and we need to visualize it. So we spent a few months writing a visualizer, and well, it was fantastic. And then we found Worldwide Telescope. This is brilliant. So Worldwide Telescope, you've all seen demos, so I'm not going to show a demo, I'm just going to cut through it. Basically, this is a picture here of all of the pieces of debris. I've got very high opacity here, but the idea is that it's showing you all the pieces of debris in orbit. And I think, so we've seen the presentations on Worldwide Telescope before, but I think there's one key point that's very advantageous for us that hasn't really been brought up, and that is this concept of exploring your data. So Worldwide Telescope lets you create a tour, for example. So for all intents and purposes, it looks like a video. The end user, I create a tour that basically takes them through my debris and shows two pieces of debris just before they're about to collide. So for all intents and purposes, it really looks like a video to the end user. difference is that the end user will look at this and they can watch the video, but at some point they may want to sort of diverge a little bit from your video. You can very easily pause this because you're actually dealing with the live data set. And you can pause this and you can start to explore around, and this is very, very powerful. So you can set a path for someone who's interested in something, then they find something of interest and they go off exploring around the data themselves, and then maybe they come back to your little tour that you've created. That's a very, very powerful feature. Worldwide Telescope, they will be demoing it on Friday. Definitely worth turning up and having a look at that. So I wanted to change tack here now. Basically, we've looked at big science. How do you spend your $10 billion? How do you monitor all the satellites? It's very expensive. Large Windows Azure project. And I wanted to change now and have a look at something very small and very cheap. And that is the Astra Project. So this is a project running at the University of Southampton. And we're using Azure in a very different way. So the Astra Project is looking at atmospheric modeling. So it's looking at getting data about the atmosphere. So this could be for weather or volcanic ash, for example. This has been happened in Europe not so long ago. And what currently happens is, like what the Met Office do for weather simulation, you get a radio sonde, it's a little box with sensors on it. You tie it to a balloon and you let go. The balloon floats off, just follows the wind, it floats off, and eventually it bursts, and that's the last you ever see of your instruments. Your instruments are streaming data back, and whilst you can see them and the weather conditions are right, you're going to get some data back. And the question comes, well, I don't want to lose my data, I don't want to lose my instruments anymore. This is a budget project, this. We want our instruments back again, because we want to be able to add other instruments into this, which are potentially very expensive. The ultimate goal of the project is looking at, we want to be able to survey a piece of space. So we have a 3D printer at the university, and we print gliders. So we have a little glider, a little airplane, we print it, 3D, brilliant, and it flies. So you could imagine that you put your instruments inside an airplane or a glider, you tie that to the balloon, and then when the balloon bursts or when it reaches a certain altitude, you release the glider, it's got an autopilot in it, and it flies home. And there's a lot of work being done. We have a glider, we have an autopilot, and there's been testing done on this. There are some rules about how high you're allowed to release from and things about the glider. But there's this intermediate bit that there was a lot of work needing to be done on this, and people were saying, well, look, we just want to test some of the instruments. We need some way of getting these instruments back again. We need something that's a data logger. We need a data logger that's got a fairly good processor in it, that knows where it is, so it's got GPS, and it needs to be able to send information back to us, and we're on a budget here. And so what we looked at doing is taking a Windows Phone 7. It's cheap, it's a commodity piece of hardware. It does all of the above very well, and it runs .NET, so I got my vote. So it does all of the above. And the interesting thing here is that, well, actually we can use Azure to work out where these instruments are going to land. So the phone knows where it is, it runs on the GSM network, it's got GPS. So what it does every now and again is it gets the GPS coordinates, it sends it straight into a Windows Azure worker. I actually have an architecture here, it sends it straight into a Windows Azure worker. The worker predicts where it's going to land, and then sends that information back to other phone devices that are tracking so basically that's us in our van. This diagram here is actually out of date. We initially had problems moving MATLAB around between Azure, so we actually went for some of the calculations being done at the university on machines there, some of the calculations being done in Azure. This was very good because it gave us this sort of an insight into a hybrid approach, which I think is here to stay. We're going to have hybrid approaches for quite a while. So it gave us an insight to that, but we do actually have the propagation working up in Azure at the moment, so it can all run in Azure. So the idea here is that we're taking, we know a lot of information about the weather of the current time when we release the object, so we can do quite good predictions as to where it's going to land. So we take our expensive instruments, we sellotape a phone to it, we tie it to a balloon, and we release it. We get in our van and we take our phones, and it says, well, we think it's going to land here. It travels a fairly long distance, and we drive and we find it. Here's the money shot. This is a Windows Phone 7 flying at 60,000 feet. That's about 18,000 meters. There's 2 successful missions that we've done with this, and there's some of the statistics about it. So you don't get GSM coverage all that way, so we're not really interested in that. As you release it and it goes up, you get some GPS information, and then you lose it for a while. When it re-enters, you have a parachute on it which slows it enough so that it can get a GSM tower and send you some more information which updates the prediction. Prediction code is fairly accurate, and if you're looking here that we're covering, we'll put it on there, we're basically covering about 100 miles at the maximum extent. So by the time it's taken us to drive those 100 miles, we'll have received new updates for this. The Astra Project is quite interesting because if you think of my previous examples, well, what are the advantages we're getting from cloud and the scalability, the burst capability and that. The Astra Project, so the Astra Project at the bottom here, is basically looking at, well, I don't know, I couldn't find a word for it, and I've called it Augmented Processing. And this is basically where we've taken a device and we're using it as a portal into a large compute resource, or you're effectively adding a large compute resource to a very small mobile device, however you want to view it. And I think this is a very powerful pattern here because smartphones are here to stay. They're very powerful. I would actually quite like to be able to steer some of my calculations from my phone. So the Astra Project is this idea of augmented processing and data dissemination. So we're sending some data back to other users. The Clouds in Space project is basically, we've discussed the burst capability, the super scalability, how we're using it to develop algorithms, and also this little bit about data dissemination here. And those are the key points that I want you to take away from this presentation. And also, cloud is here, and it is changing the way that we're doing science. Before I open up for questions, I included, you're going to be able to get the slides, I included some links about the projects and some of the tools that I use that may be of interest to you. So I'm just going to flick through these, but you do get the slides, and they're included in there. So I guess the last thing I really wanted to basically say is that on Friday there will be a demo, and feel free to come along and speak to me then. Otherwise, go and pester the guys at the Worldwide Telescope guys. It's really, really interesting. I think the only downside with the Worldwide Telescope is that it turns out the universe, it's really big and it's really interesting, and I spend a lot of my time flying through the universe rather than doing the work I should be doing. But I see that as a bonus. So we'd like to thank, obviously, Microsoft for their support, and obviously this isn't all my work. There's a team of people at the University of Southampton that work on this project, and I'd like to thank you very much and open up for questions.
Do we have any questions? Come around. I've got a couple of questions, short questions. The first one is that, could you please elaborate a little bit on the table method of data storage in Azure? And the second one is that if you know any implementation of biological or molecular biological data using Azure.
Okay, so the first question is basically tables in Azure. Really interesting and really fantastic. Basically, you have a key and a primary key and a secondary key, which lets you uniquely identify a row. I think it's worth mentioning actually maybe a little bit about how this works conceptually. So the primary key you can think of as a bucket, and the secondary key lets you pick out the row in that bucket. And the reason why table storage scales just so well is because these buckets, you can move a bucket to another machine. So they're running this all on Azure here. So you can take a table. You don't have to worry about this. This is how it works underneath the hood. For you, you just have a key and a primary key. The reason I'm mentioning this is you have to pick those very carefully. So your primary key is the bucket. And the idea is then that underneath the hood, that this all the data that lives in one bucket can potentially live on one virtual machine. So bear that in mind. Don't put everything with the same primary key. And that's the only indexing you happen to have into a table, which is why I think table and people think SQL table gets difficult. Transactional support, there wasn't any. It's been added now, and I don't know the status of it, but it went along the lines of you can have a transaction provided it only stayed in one bucket. So this concept if it used the same primary key. So that's very limited, and that's pretty much all you have in the way of transactional support. You don't have transactional support currently, as far as I know it anyway, between multiple tables. So you can't add things into two tables at the same time in a transaction. But you don't really want that, because what you're doing is you're trading off all this heavy, expensive transactional support for something that's very fast and will scale very well. So imagine if you've got your primary key and you've distributed that primary key very well, your list, your table can grow almost indefinitely. The second part of your question was about biological applications for this. I'm afraid I'm really not the man to speak to about that. Sorry.
Going to the 500,000 1 centimeter object, how are you going to find it? Because
So the question...
A ground-based telescope can't see something.
That's brilliant. So the question is basically about the pieces of debris that we're tracking, and the desire to track this 500,000 pieces of debris that are 1 centimeter or greater, and how is it being done? Yes, ground-based stations have very limited capability in that aspect. I think there are some optimization that they're hoping to apply there, and we're using more ground-based stations. Bear in mind this is SpaceTrack that deals with this. But there's also discussions now as to whether you should start to put sensors on satellites. And maybe you should actually have some cooperation. So, people own these satellites. If I owned a satellite, is it in my interest to tell you where it is? People don't really like other people to know where all of their satellites are, for example. Yeah, you can see some of them. So, so there's definitely an issue there. And so, there's a lot of work going on into changing how we can actually reduce the size of these objects that we can currently monitor. And that's SpaceTrack that's working on most of that. Oh, one more.
Can you comment on the compute resources that you actually used in the cloud to track the data that you were able to obtain? And if, not about financial side, but about, the number of nodes or the amount of processing time required. And then, assuming you could actually see the 500,000, how much scale you would expect to need?
Yeah, interesting. So it's very much an ongoing project. We currently use a very small number of workers, so we don't exceed 20 workers at the moment. But that's mainly because we're only pushing small pieces of the catalog through so that we can test each of these stages. So in the architecture diagram, we're basically down at the bottom left-hand corner where we're getting to the stage now where we're going to be spitting out this catalog of satellites that we want to remove. So the project is very much work in progress, and we don't need to monitor, we don't need all this live data yet. So we're only using a subset, and yes, we're not exceeding 20 workers for the time being. However, within the next month or so, we're looking at ramping this up significantly, and I think this is where it's going to really show how well it scales. So we're very lucky here. This problem is embarrassingly parallel. You've got a collection of objects, does an all comparison runs as parallel as possible. And so I think our scalability results will look very good, but they're very biased and they're very specific to the problem that we have.
One more question.
¿Existe algún sistema de rastreo no de residuos artificiales por el hombre, sino de aerolitos que no se desintegren al chocar contra la atmósfera y que puedan tener algún impacto sobre alguna ciudad?
My Spanish, unfortunately. Anyone willing to help me translate on that? My Spanish is very limited, unfortunately.
Perdón. Is there a tracking system, not of artificial, meteorites. No, but he wants to know if there's a tracking system for meteorites, not man-created things floating out in space.
SpaceTrack does have some meteorites in it, but they're obviously not updated as frequently. There are some places. SpaceTrack is a good place to get some of that information if you're particularly interested in meteorites. I'm very much on the sort of the technology side of things, so for the applied science, I can certainly put you in touch with someone that would probably be able to answer that question better than I can, to be honest.
Well, we are now going to take a break and resume at 10:30. Thank you all for coming, and thank you, Stephen, again for your presentation.
Thank you very much.